Hello. So yeah, I'm a second year PhD student under supervision of Dan. So Dan was here last year and did a sort of similar talk. So I hope this isn't rehashing too much. This is sort of the story since then. So normally we reason about hardware by using simulation. We give some values in, we run this simulation, and then we get an answer. But what if we were to approach something using syntactic reasoning, not reduction based and step by step down? That way we could get an alternative approach to reasoning about hardware. We could do an operational semantics for digital circuits. So we're taking an approach that's rooted in monoidal categories, the scary world of category theory. So how do we build a circuit categorically? So we define circuits as morphisms, or building blocks, in a symmetric traced monoidal category. So what are our base building blocks? Well, we've got these values that form a lattice. So we have a bottom element, this disconnected wire. We have our two middle ones. We have true and false. And then right at the top, we've got this top element, this short circuit where everything goes wrong. And then obviously we have gates as well. We have we have two inputs and one output, or maybe a multiplexer, 3 going in and 1 coming out. And also in our circuits, you've got to have these sort of structural combinators. We have a fork. So we take one element, we get 2 out. We can join 2 wires together. Just cap off a wire, get rid of it. And also we have just a wire, just something goes in, we take the same thing out. So how do we build up our circuits from these blocks? They're not very useful on their own. Well, we can compose them. We can compose them sequentially. We have something here. Can't see my hand. Something here. Something here. We can put them together to make F followed by G. And we can also put them on top of each other. We have a one here, one here. We can do F until tensor G, F on top of G. So we can also swap over wires, because otherwise everything would just be like not particularly useful. So we can just swap them over with what this thing is called a symmetry. And symmetry, it's quite interesting. We've got some axioms that the symmetry all has to follow. And we have, say, an F and we have a G. We can also push them through and sort of put G on top and F. That's naturality. And also, if we put 2 symmetries next to each other, then we're going to get just 2 straight wires because they just sort of untangled the mess. So here's a sort of little example. We can make something like a half adder. And you can see already these sort of terms, and they're getting quite messy. Like what is going on here? So like, you can't really tell. So already we're seeing that perhaps something more diagrammatic, something like this, is more appealing. So let's keep that in mind for a moment. So far everything has been sort of combinational. We just have some values and we get something out of them, and that's not very interesting because I mean this is synchron. We want things to be synchronous. So we can introduce a delay morphism, delay block, and that's parameterized by this sort of time monoid, kind of like a 1 second, 2 seconds, whatever you want. And this delay, we can just put it in our circuits to show where the delay is. And the other sort of element we might want to put in is feedback, and that's using a trace, which is the traced part of this symmetric trace monoidal category. All this means is that we take the output of a box, a circuit, we loop it around, and we connect it back to the input. This also has some more of these sort of structural axioms to make sure everything's well behaved. If we have a long one, we can make it a short one. We have a sort of a loop, we can go yank it out and get rid of it. It's just a line. If we have one that goes on a long one, we can just sort of suck it in a bit. And then if we have sort of some tangled up ones, we can untangle them, make it just a nice normal one. Then, so again, an example, we have a flip-flop in these feedbacks just to show that things are going back with delays in place. But again, what's this all about? What is this expression? I can't read a flip-flop from that. That's nonsense. So it makes very little sense. So we want to just, have another diagrammatic approach. So before we sort of move on to this more formal diagrammatic thing, we've got to think about how are we going to reason about these circuits in these operational semantics. So we define the structure of our circuits, sure, but great. So we've got a circuit. What are we going to do with it? So we need to introduce some more axioms, these behavioural axioms, to represent what the circuit is. So one example you could do is say if you've got two truths and you pipe them into an AND, well, that's just true, isn't it? So we can identify these redexes in the term, and we can just reduce them. So you have that's a true, then we can replace that again with a true, and then finally do true. So great, we've done it. We've got a really nice operational semantics for digital circuits. But what about if we had something like this? Now, this is still the same thing. We still have these four truths going into these two ANDs, but the redexes have completely vanished. And that's quite annoying because to identify these redexes, well, you need to use lots of commutation to rearrange stuff and apply various structural axioms. So we need an efficient way to identify redexes. And that's another reason why we might want a formal diagrammatic approach to do semantics. So we've been using these informal diagrams in the past few slides to sort of illustrate what these terms mean. So why not we actually formalize these completely into a sound and complete diagrammatic language? And that's exactly what we're going to do. So the diagrammatic language in question is hypergraphs. So all a hypergraph is just a graph, we've got vertices, but rather than edges connecting two nodes, we can have these edges, these boxes, to connect an arbitrary amount of vertices. And these boxes have sources on the left and targets on the right. So the source of, say, this edge is this one, and then this edge has these targets vertices here. Obviously, these arrows represent what's connected to what. So we can already see how these hypergraphs might relate to these informal diagrams I showed earlier. We have our boxes to represent our gates or whatever, and then these sort of vertices represent the wires between boxes. But we might already see we've got some problems. So vertices and hypergraphs can connect to any number of edges. But obviously in our circuits, we can't just split wires at will. We have to use these explicit combinators. So we might need to consider that. And also we want to keep track of the inputs and the outputs to our circuit, because otherwise we wouldn't be able to know what to give something, like we wouldn't be able to do anything. So to fix these problems, we're going to use a restriction on our hypergraphs, and we call these linear hypergraphs. So you see, linear hypergraphs look very similar to our normal hypergraphs, except now each vertex can only have a left and a right connection. That's why they're called linear, because there's one this way and one that way. And also, then we have these special edges, these input alpha edge and this output omega edge, just to keep track of all our interfaces and what's going in and out. So if we have these hypergraphs, we can embed sort of subgraphs into other graphs by using a hypergraph homomorphism. And all it is saying if we have, say, this one here, this F, we can then sort of put it into this bigger one here by doing maps between the vertices and the edges. So here we see this one goes over here, goes there, and the F goes into there. And if these maps are bijective, then we say that the two hypergraphs are isomorphic. We do perfect maps between each one, and they're basically the same hypergraph as far as we're concerned. So we have a diagrammatic language. Great. So now we need to show, is this language a sound and complete language for digital circuits? And what do we mean by this? So we want to use them, as I said, as a graphical representation. So to show that this language is a sound graphical representation, we need to show that any terms in our language, in this term language, that are equal, when we interpret them as hypergraphs, they're going to be isomorphic hypergraphs. So we don't start making things not equal when we draw them out. So we translate our terms into hypergraphs with this interpretation sort of function here, these brackets. And if we have just a gate, we say, fairly obviously, that a gate is just an edge with the appropriate numbers of sources on the left and the targets. So this AND gate has two inputs and two outputs, or one output even. And then we can combine these hypergraphs by sticking them together, just like we did before with our sequential and parallel composition, and building much bigger hypergraphs. So for example, we have this term here into this hypergraph here. So we have this sort of, again, this join edge on top of this F, swap over the wires. We have this fork and an identity, and we trace it all so everything goes around back there. So is this sound? Well, all we need to do is make sure that the structural axioms that I showed earlier, the things like with the things crossing over or the trace going to be a big one, we need to make sure they still hold in the language of hypergraphs. Unfortunately, they do. You have to take my word for it. It took a long time to prove, and it wasn't that interesting, but that was the start of lockdown for me. I got it done. So now we can show that we have soundness, and if we have terms f and g, then if we interpret them, they're still isomorphic. That's one half our job done. Excellent. We need to go the other way now. We need to show completeness, show that we can recover these terms from a hypergraph. There we go. If we have a unique term up to these structural axioms again, that when you interpret it again, it's the same hypergraph. So this is a little bit, say, more complex than just banging in axioms and making sure they all work. We need to make sure we have an algorithm to get out this term. So how do we do that? So first, there are two steps to this. First, we have definability, which is that we have a method of some sorts to get a term from a hypergraph. So how do we do that? Well, first of all, we get our hypergraph and we see our edges and we set an order on these edges. So this one first and this one second, and then we just stack them up in this parallel tensor that we saw earlier. We have this one on top of this one. And then what we do is trace everything around. So we have it back on the left. We have now this trace, and then we have this gap. And what are we going to put in this gap? Well, what we need to do is make sure that these edges, all the outputs connect to the right inputs of other edges. So what do we do? Well, we just shake everything up with various of these symmetry morphisms, make sure everything connects up correctly. And if you're feeling like particularly bored on this Friday morning, you can just follow the wires around and make sure this is all correct. Let's just see. Formulas there. Yeah, it does. So we're just assuming the rest of them are also correct because I took a long time making this diagram. I don't want to make it again. So this means that we have a term from a hypergraph. So we have this definability. They might be thinking, but hang on a second, you just selected this order on the edges, like surely you're going to get lots of different terms out of it. But fortunately, whatever edge we choose, whichever edge order we choose, we're actually always going to get the same term out of it. That means we also have coherence. And then we can conclude from that that any hypergraph has a unique term. That's good. So now we say we have a sound complete diagrammatic language for digital circuits, and we can reason purely graphically. And now, if we need to find redexes, we just find them in the graphical notation, rather than having to look at this term and try and pick them out. So now we have this diagrammatic language. Well, what are the semantics of digital circuits that we can represent in this way? Well, so first of all, we have our gates, which are extensional, so only affected by the inputs and the outputs, and monotonic, so they respect this order of the lattice of values that we said earlier. So if you get some amount of inputs to a gate, you can transform them into some other value, and that's always going to be that value. Like I said before, we have true and true going into an and that's just can be replaced with a true. If we have a fork of a value, we can just duplicate them. We have a join. We can then take again this least upper bound defined by this lattice we said earlier. So maybe a true and a true would go for a true because we're on the same level. But if you've got a true and a false, then they'd go to this sort of undefined top element because that's just a short circuit, isn't it? If we have a stub, well, we can just discard it because it ends. We don't care about it anymore. Now for delay, we've got some slightly more complex axioms. So if we've got a delay followed by a gate, then we just sort of shift it to the other side because we don't really mind if we delay the start of it or the end of it. It's still going to happen at some point. Then perhaps one of the more interesting ones is this streaming axiom. So we have something happening now, and then we have a load of stuff happening later for this delay. Then we can actually put this gate up, we can duplicate it into two and process this bit now, and we have all this stuff can be done later. And that's quite powerful when processing, say, a stream of values over time. And you've got, say, one, and then another one, another one. All you need to do is do each one separately with a separate gate. So the last thing we need to work out how to represent is feedback. And this is slightly more complicated than just whacking in axioms, as we need to make sure we have a way of unfolding this feedback and doing over and over again in recursion. So before we look at that directly, we need to generalize these fork and stub combinators. They can work on things of arbitrary length. So we have this diagonal morphism now, so we can just copy anything, and we have this erase, which can just delete anything. And this is called the product, and means that we can now make use of the naturality axioms. If we have something, again, we can just push it through, duplicate it, and if we have something which is in all stubs, we can then forget it all again. So the combination of the trace and the product is quite interesting because it means that we can use what's known as the iterator, which is how we can model recursion. So the iterator is just when we take all the outputs from some circuit, we feed them all back into the input. And why is this useful for us? Well, it means that we can use the unfolding axiom, which is how we can sort of copy this circuit, put it to the side, and have the first bit here, and we keep recursing over and over, we keep unfolding, and we get some sort of result out of it. So we have all this massive long list of redexes. So how are we going to apply these? Well, that's by using graph rewrites. So what is a rewrite rule in the language of hypergraphs? So this is a span of these hypergraph homomorphisms I mentioned earlier, these embeddings, where we have the left-hand side of the rule on the left arm of the span, and the right-hand side on the right. In the middle here, we just sort of chop out any of the content of the rules, as it were. So we have their common interfaces in the middle here. And we have, say, this set of axioms, these circular axioms, we can just write them with this bracket notation to show that we've converted them all into these spans of hypergraphs. The very common framework when doing graph rewriting with these graphical combinatorial structures is called double pushout or DPO rewriting. And so let's just go through an example to show how we might use that with one of our axioms. We have this man again. We have this term, and as you can see, this term has got this diagonal copying pass in it. We know that we can push through this F to the other side and get the doublet. So how do we do that with a double pushout framework? So first of all, we have our rule span here again, if you remember. First of all, we need to identify a matching of the left-hand side of the rule inside our term G. This is just done by a hypergraph homomorphism again. We show we can embed this part of the rule into our term. And we also, just to make sure everything stays sort of sane and doesn't fall apart, we need to have this again, this common interface here, just to make sure, or when we do our rewriting, everything stays the same. So now that we have this sort of side here, now we can construct the other side of this square. And effectively, this hypergraph C is G, but with the L bit cut out of it. So we're preparing for a rewrite. We're chopping out the bit we don't need anymore, and we're about to stick in the next part. And that's exactly what we do with this next step here. Sort of finish off this diagram, and we paste in this R into this gap here, and then we have our finished rewritten term. It's very simple. And then we write, say, G squiggly H if we can perform rewriting in this way. That sounds very good. Sounds like we've got a nice system here where we can always do this sort of rewriting. But sadly not quite as simple as that, because the key part of this process is that this element here, this part of the grid, this push out complement, this bit needs to be unique. Because if it's not unique, then we might start getting some really weird hypergraphs on the line, and we don't want that. So we need to make sure that this push-out complement is unique. And how do we do that? Well, there's this framework called adhesive categories, and there's many properties that these satisfy. These like, oh, you can always do these sort of push-out constructions. But the main part is that these push-out complements are always unique, and that's what we want. But unfortunately, Our language of linear hypergraphs may not be an adhesive category, but it is what is called a partial adhesive category. And this means that the pushout complement is unique for a certain class of spans. And fortunately, that includes our rewrite rules. So that's it. We've got it. We know that we can always do this pushout complement construction and then achieve the right-hand side of our rewrite rule. That's good. So just to sort of wrap things up, what are the sort of things that we can use these rewrite rules for? Well, we have these things called cyclic combinational circuits. We say, oh, we've got these feedback loops and whatever. And you might think, oh dear, we have these feedback loops. There's going to be a problem to simulate or use or whatever. But actually, with circuits like this, the feedback isn't actually feedback. It's just a way of sharing resources. And the way that these multiplexers are set up is that actually they all reduce down. If you give a value to a C, you might just reduce to this circuit here. And with our framework, we can do this. And then also we could apply it, say, to pre-logical circuits. So we just define this sort of massive thing with all these very low-level, transistor-level things. And even though that's just slightly lower level than digital circuits, well, we can still apply it, apply our rules to it, eventually get down to some smaller sort of term. So what have we done? So we managed to define this combinatorial graphical language for symmetric, trace, and monoidal categories, or the language of digital circuits, and we've shown that it's sound and complete. And this allows us to reason about circuits purely graphically, which is good. We can find our redexes and we just go, oh, reduce, 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 rather than trying to mess around with these terms, which are long strings of characters doing who knows what. And even when we add behavioral axioms to the frameworks, not necessarily these ones which are automatically fulfilled by drawing them, we can still reason graphically by using graph rewrites, because our linear hypergraphs form a partial adhesive category, so the graph rewriting process is well formed. So all we need to do is formulate our digital circuit axioms as these rewrite rules, these spans of hypergraphs in the language of hypergraphs, which then of course leads to a question. Do we have all the axioms for digital circuits? Do we have a sort of complete set that we can reason about all kinds of behavior? And we don't think we have quite yet. There are some circuits, or especially some with feedback with instantaneous delay, where we're not quite sure whether we have everything we need yet and what we need to do. So that's sort of the next step in this quest for a diagrammatic semantics for digital circuits. Yeah, thank you very much.
Thank you very much, George. Any question? So let me check on the Slack.
Here is Robert.
Yes,
Can
go
you hear
ahead.
me? Okay, maybe I have a crazy question. It's not that important, but can you say something about graph planarity? The fact that lines may cross one another, and which of your transformation may preserve this, which of your transformation in one way may introduce crossings or remove crossings going in the way? Because your hypergraphs almost look like layouts. And planarity is important in in circuits layout.
Well, see, in the term language, so you've got this sort of express sort of symmetries and stuff, so things can cross over. I think obviously they're still going to be retained by the hypergraph, because eventually you'll have to cross them over. Say if you have a gate and then the outputs cross over, they're going to have to cross over. I'm not as sure, say, things are going to introduce or remove or whatever. I haven't thought about that as much. Is there anything you had sort of in mind, or?
No. It was just a crazy question. So that has to, because.
But it's something to it's something to think about. Yeah.
Okay. Thanks.
Tim, do you have a question?
Thanks, Benoit, and thanks, George. I wonder, would you mind going back to the slide with FNG?
That's quite a lot of slides. This one here, or?
This one. And if imagine, so your FNG can have internal state, I guess. And if you wrap that whole thing in a recursion operator, will you be duplicating the FNG? And how do you kind of keep track of the idea that each of them represents an instance?
Well, the idea sort of with this sort of examples, if you give one, is it nothing's being duplicated here because there isn't actually feedback. So you just give some value here, and then the flow would just go like this, sort of follow through. So nothing here is really being duplicated.
Oh, I meant, sorry, I didn't ask the question very clearly. So imagine if f and g were both counters, somehow they add their input to an internal state and put it on the output. And then I wonder if you did wrap this whole thing in some kind of recursion, would you duplicate the internal state of the counters, or would you somehow respect the fact that there's only one state, one register inside f and one register inside g?
Oh yes. Oh, is Dan trying to say something? He's coming in.
This is just for combinational, FG combinational circuits. This is about combinational feedback. So that's why it says cyclic combinational circuits. If F and G have delays in them, then the unfolding would be different.
I see. So you're right. I didn't pay attention to the heading. And do you have some kind of typing then? That means you can only apply rules to the combinational circuits, and you have different rules for the sequential ones?
No, it's just in the to apply the unfolding of the feedback, you have to bring the circuit to a normal form.
Okay.
I'm not sure if George had that had kind of the general unfolding rule. Like it's quite complicated,
Yeah, I didn't put in the general.
but you need to bring the circuit to a global form in which you make all the feedback global and you make all the delay. Like you just have to put it in a particular form so that the unfolding can work. And whatever is left has to be combinational. So here F and G are combinational.
Okay, thank you.
Okay, thank you. Thank you, George. I think it's time to move to the next talk. So the next speaker is Marino